We were looking at image enhancement yesterday, and there are a few sections of that chapter left before we switch to a different topic. I skipped details of this image, so I'll go back to this image where we have an MR image of the knee joint. It doesn't matter what it is, some image. And when you apply an ideal high-pass filter, you are extracting only edges. Even if you apply a Butterworth high-pass filter, you're only extracting edges. You see that the intensity information is lost. Bright area here, dark area here, they all have the same value. And this image actually has positive and negative values, and that range has been mapped with the negative value to 0, the minimum value to 0, maximum, which is positive, to 255. So this is 0 in this image. So anything darker is negative, anything brighter than that is positive. So you see the edges, but you also see these disturbing ringing artifacts. In some of my other images, I had to do zero padding because of the size of the image being some odd shape or some different numbers other than a square. So to compute the DFT through FFT, I had padded zeros, and the borders also gave some ringing artifacts. In this case, the ringing artifacts are clearly related to these edges that are present in the image. There is no ringing from the edges of the actual image array. The Butterworth filter has given you the edges here clearly without the ringing artifact. That's the advantage of having a monotonically decreasing or increasing function in the frequency domain. If you have any abrupt transition, like an ideal filter, there will be ringing artifact. This is high frequency emphasis. So intensity information is retained. What is white is white, what is black is black. But there is some sharpening because high frequency components were boosted. So some of these black spots, whatever they are, and the edges are stronger. This projected image doesn't show it, but if you look at this on my screen, it is much better. That distinction is clearer. So you could see that when you look at the PDF file and zoom in. Now, there is another interesting technique that was initially developed by Oppenheim and Schaefer and their colleagues called homomorphic filtering, where the operation that combines the components of the image will be converted from whatever it is to addition, and then linear filters are applied. And for image contrast enhancement, that gives some interesting advantages. So let's look at homomorphic filtering for enhancement, and I'll explain what exactly that enhancement is as we go through. So consider an image that is a product of two functions. Gxy is fxy times sxy. I mentioned that earlier. When you take a picture of me, for example, the picture you get is the product of the illumination function, the light that you put on me or the light that is coming from wherever, and my reflectivity pattern. What is reflected? Black areas don't reflect much, lighter areas reflect more. So my reflectivity pattern is the actual information. The light source is expected to be uniform. But sometimes it is not uniform. There could be some non-uniform illumination. The light source may have some irregularities, or there could be some shadow, dark portion and light portion. In such a case, this function Sxy, which is the illuminating field, is not uniform. And what you want is Fxy, but Gxy might not show Fxy clearly because of variations in lighting that is not desired. If you take the Fourier transform, GUV is FUV convolved with SUV. So the spectrum of the image is completely messed up through convolution, because you know convolution, one function goes on top of the other, and then the product is integrated over the entire frequency range, and you move and do that for every point. The spectra have conjugate symmetry, so reversal is not important for convolution. So this operation spreads or smears the spectrum of the original signal by the spectrum of this SUV. Now if SXY is constant, then SUV is just an impulse. So convolution with an impulse doesn't have any effect, so there is no problem. You actually get the real image. So a uniform lighting source will give you the original image. And there are cases, of course, if the picture is passed through a linear shift invariant system, then it gets convolved with the impulse response of that system. And then GUV is HUV times FUV, multiplication. The input is convolution. After transformation, it is multiplication. So how do we separate F from H? Or in this case, how do we separate F from S? Is a question. You cannot apply a linear filter directly. You cannot separate them by any of the methods we have seen so far. So what Oppenheim and Schaefer said is, let's develop a technique known as generalized filtering, linear filtering, where you convert that operation that is combining the two things that you are interested in, or that have combined to give you the image that you have on hand, change that operation to addition. And then you can apply linear filters. And hopefully their separability in whichever domain you go to later on will still be maintained. That is not guaranteed, but hopefully it will work. And the reason for this is linear filters are well established. Fourier transform is established. All the filters we have seen so far, they're all well known and we want to use them. That's what we have in our toolbox right now. So it is attractive to consider extending the application of the linear filters and other techniques we have, but we need to convert that operation to addition. So multiplication and convolution need to be converted to addition. And this is known as generalized linear filtering or homomorphic filtering. So take this multiplication. To convert multiplication to addition, it's very simple. Take log 10, log E, whichever you like. So log gxy is log fxy times sxy is log of f plus log of s. So that multiplication has now become addition, but there is a log, and hopefully the log will not affect how the two are interacting in the frequency domain, because next we want to take the Fourier transform. If the two things are added, take the Fourier transform, which is linear, their spectra will be added. Linearity is maintained. The requirement is that these are not zero because you're taking zero, so you may have to add a bias or something. Then GLUV, because there is a log here, we will put GL here. GLUV is FLUV plus SLUV. The spectra of the log of the signals or images are now added. So assume that the log transformation has not affected separability of the Fourier components of the two signals. I say signal, image, same. So a linear low-pass, high-pass filter can be applied then. And then you can select or selectively emphasize or de-emphasize one of them. And then an inverse Fourier transform will give you the filtered image, and there was a log at the beginning, so you have to reverse that using exponential. So the image here is treated as the product of an illumination function and a transmittance or reflectance function. When you take my image, it will be reflectance. If you have a transparency or looking through like a transparency projector, for example, you don't use that anymore. I suppose we use the HDMI connection nowadays. But in a microscope, if you are putting light through some specimen, then the light source is multiplied by the transmittivity of that specimen, which is like a pathology slide. So that's the model. But if the lighting is non-uniform, then your information of the image is somehow distorted, and you want to remove that. And there could be large dynamic range. Like you saw in this MR image, there is maximum brightness, minimum brightness, or maximum darkness there. So the dynamic range is there. but the contrast may not be present. In this case, there is good contrast, but maybe not here. So by emphasizing higher frequencies, we can increase the contrast of such details. But dynamic range is maintained, and in some cases you may want to suppress the dynamic range. It's blinking more often today. So high emphasis filter leads to simultaneous dynamic range compression and contrast enhancement. What is assumed is that the sharp details in the image are in the higher frequency zone of the Fourier transform. And the variations in the lighting source are not so rapid. They could be slowly varying, and hence their spectrum will be of a lower frequency, very, very low frequency range. So you suppress the low frequency and increase the high frequency, which is high emphasis filtering, after taking the log. So the sequence of operations is input image where the entities F and S are multiplied, apply log, that multiplication turns to addition, apply the Fourier transform, they are still added, put a linear filter, they are still added, inverse Fourier transform, whatever filter you have done there, and then the inverse of that, and then they are still linear, and then exponential would turn addition to multiplication, back to the original domain, and the same relationship as at the beginning. So this linear filter is now in the frequency of Fourier space. High emphasis filtering could be done, as I showed earlier, take a Butterworth high pass filter and boost it up but with a bias so that the DC gain is not zero. So we go back to my grad student Mauro's daughter in the snow cave. I had to adjust the image a bit to prevent artifacts and make it a square image. So there is dynamic range. Bright, maximum 255, and dark 0, and she is there, you can't see her in the original image. So stretching doesn't help because it's already occupying the full range. But you can stretch a selected portion. I think I showed that earlier, by taking a small portion corresponding to this range of grayscale only and stretch, then you can see some details. But that doesn't enhance the contrast. It only enhances the visibility by a linear transformation. Now here we have the log of the original. Just taking the log will compress the dynamic range. And the difference between the bright area and the dark area is compressed, and then when you stretch it back to 0 to 255, that intensity is reduced and this is increased, and you can see the details, but there is no contrast enhancement. So this is a nonlinear stretching of nonlinear compression operation, log of that. That's all. C is homomorphic, including with a Butterworth high emphasis filter. So now you see there is contrast enhancement. If you look at the lines, the sole of her boots, then these lines are stronger. That string you see there is clearer, her face is clearer, sharper. So there is contrast enhancement, there is sharpening of the details because of the high emphasis filter. And the illumination field, which was very bright there and very low there inside the cave, that has been reduced, that range has been cut. So the dynamic range has been reduced, but then we stretch it back to 0 to 255. All of them are mapped to 0 to 255 for display purposes. But what does 0 correspond to and what does 255 correspond to in the original scene? That is different now. So is this better than that? Well, if you're interested in what is inside the cave, yes. If you want to see the snow, then no, that is all washed out. So there is give and take. Something is improved and something else is lost, because the dynamic range has been compressed. Contrast has been increased. So if you apply only the log, you get that, which is not bad, but no sharpening. If you apply only the Butterworth high emphasis filter without the log operation, you get this, which is not this. So both of them are important. So only log, only Butterworth, the same Butterworth high emphasis, they are not giving this kind of a result. So this was originally proposed by Oppenheim and Schaefer, and you will see in their DSP book and their original papers. So the Butterworth high emphasis filter is this. The gain at 0 is 0.1, and the maximum gain is at half the sampling frequency. So this is that calcification image I showed earlier. There are calcifications in bright parts and in some dark areas spread over there. It has good dynamic range, but the calcifications are not sharp. Log, it hasn't increased the contrast. The dark areas have become brighter. The bright areas have remained bright. This is homomorphic filtering. The dynamic range has been reduced. The difference between dark and bright has been reduced. But the calcifications now are a little sharper. Compare that with this. You can see these calcifications better here. This is with the Butterworth high emphasis only, which is not bad really, but this is what homomorphic filtering gives you. Okay? Simultaneous compression of dynamic range, which was excessive in the previous case. That's excessive dynamic range compared to what you want to see. Your detail of interest is suppressed too much. And contrast enhancement or sharpening. There is an extension of this to convolved signals. When images are convolved, let's go back there to that equation. When they're convolved, how do you convert convolution to addition? The first step is already here. Take the Fourier transform, convolution becomes multiplication. And how do you convert multiplication to addition? That's what we saw just now, log. So the rest of the story is the same. So if you want to separate convolved signals, which is deconvolution, that I have in a different chapter, you can get that from the book. It's the same sequence with a Fourier transform at the beginning. So the Fourier transform first to convert convolution to multiplication, take log, and that becomes addition, and then you do a filter, linear filter, and then reverse the Fourier transform, reverse the log, go back. Okay? So that is homomorphic filtering. There are more details there. Homomorphic signal processing has been applied substantially in speech signal processing and many other biomedical signal analysis applications. But in image processing, this is done. This is the application. Deconvolution is also possible. That is in a different chapter. We won't look into that in this course. Okay? Now we were interested in adaptive contrast enhancement, and our main idea to begin with when we started this investigation of adaptive neighborhood image processing, which I showed earlier for noise removal, was actually contrast enhancement. So when I joined Dr. Richard Gordon as a postdoc fellow, he was interested in adaptive contrast enhancement of mammograms, because mammograms have details that vary substantially in size and shape. So if you apply a 3x3 filter that performs edge enhancement, radiologists rejected such images. They said these are not good. There were a few other techniques proposed, and most of them caused edge enhancement and edge highlighting, which radiologists did not like. So we started exploring this notion of adaptive neighborhood processing, where for every pixel we grow a region to adapt to the detail that is present at that location of whatever size and whatever shape. I showed that adaptive region earlier with that mountain and snow on the mountain. So we started with mammograms. And interestingly, although it was a very short paper and the illustrations were not that particularly good at that time because digitization was poor and display was poor, but still that paper has many citations and has been well received long ago, from 1982 or 83. So the background is diagnostic features in medical images, especially in mammograms, vary widely in size and shape. A tumor could be large, microcalcifications are very small, almost like a dot, a couple of pixels, a few pixels wide. The shape could be anything. There are ducts and ligaments and many other tissue patterns of different size and shape. So classical image processing or enhancement techniques cannot adapt to these varying characteristics. Now, or after we did this, later on wavelets came and multi-scale image processing came. So I'm talking about the 1980s when image processing was still 3x3 and Sobel mask and such things. The application of a global transform or a fixed operator to an entire image yields poor results. We tried that and we know that. So therefore it is necessary to design methods that can adapt the operation or the pixel collection used to derive the output to the local details present in the image. The operation is one thing. The other thing is, what is the population of pixels you are using to perform that operation, like the mean 3x3, 5x5, and you saw the various shapes of neighborhoods. But we can use any bunch of pixels. How did you get that bunch of pixels? And what kind of a filter, mean, median, and so on. So the operation needs to be adaptive. The population of pixels collected for the current pixel being processed should also be adaptive. So we call this adaptive neighborhood contrast enhancement. I'll skip the flow chart. What do? The first pixel in the image is taken as the seed pixel. Seed means that's where we are starting the process, and the output is applied to that pixel. And every pixel becomes a seed in its turn. The immediate neighbors, 8 connected or 4 connected, are checked for inclusion. If the difference between the seed and the current pixel and is less than a threshold or the ratio, this is like a contrast measure, F minus B over B. We saw that simultaneous contrast. This is a measure of contrast. If that contrast is less than some tau, it is normalized. Then we say, okay, include that pixel in the region and keep growing. If you include a pixel, then you check its neighbors, and then its neighbors, and so on. So the region grows. If a neighbor's gray level is within the specified deviation, it is added or appended to the queue. And you check if it is not already in the queue. If it is already there because of some other path, then you don't have to do it. A pixel is taken from the start of that foreground queue, and then that becomes the current pixel, and its 8 connected neighbors are checked, and so on. The region grows. If a neighbor's pixel doesn't meet that inclusion criterion, then it is marked as a background pixel. Background means it is not in the object. Background is not necessarily outside, but there could be parts inside also that are not included in the region, because those pixels have different values. Now we have different criteria for this. We have modified this algorithm depending upon the application, and I'll mention a few later on. A background indicates that a border has been reached, but not all objects are compact. There could be holes inside, and those holes have borders. So the border could be inside one big border also. So once all of these neighbors have been checked, the program goes back and then checks the connected neighbor pixels of the next pixel in that queue. And they're all processed until region growing stops. No more pixels can be added to the foreground region, or you may say, well, if it has grown so much, then that's enough. So you have to put some conditions so that you don't spread over the entire image. So the borders of the foreground then are expanded in all directions and molded in shape to get an overall ribbon around the object. And I showed that also on that snow on the mountain earlier. And that is the overall background for that object to get a contrast measure. The contrast is computed. So we have some region that could be of any shape and size, and there could be some gaps in between also. And around that, we grow a border, and that is the background. This is the foreground. So we do this F minus B over B. Now that is the contrast of the object. It doesn't have to be an entire object like an entire tumor. It is something in the image that is a pattern. What it corresponds to, we don't know at this time, and that's not my job. I just want to find what is the contrast, and if the contrast is poor, I want to bring it up. So there are a few parameters for the seed-filled region growing, the growth tolerance tau. And we put some conditions. The seed-filled region growing results in regions having contrast greater than some minimum, C min, let's call it. So this minimum contrast should be independent of a region's gray level, and enhancement then will be independent of a multiplicative transformation. That's why you take the ratio. You're not just taking the difference, but the ratio. So a region with minimum positive contrast C min will have a minimum foreground value of F and a mean background value 1 minus tau F. Tau is that tolerance. So what is the contrast then? The contrast is tau over 2. If you work out that F minus B over F plus B. Oh, I wrote that. There is another definition where we use F plus B. There are two definitions of contrast. So if you use this definition, it is tau over 2. So the minimum contrast is independent of the foreground gray level and depends on the tolerance used for region growing. So we saw earlier Weber's ratio and the just noticeable difference. The just noticeable difference, or JND, is 2%. So it suggests that the growth tolerance should be about 4%. If you want to capture objects that are just at that JND level. So they are barely noticeable prior to enhancement, and after that they'll be enhanced. Anything lower than that is considered to be noise or internal texture, and we don't want to modify that. Or we don't want to enhance noise in particular. So this is an analysis of how tau, that region growing tolerance, may be related to contrast. So contrast enhancement, we have used this measure because if you divide by B, if B is 0, then there is a problem. That is unbounded. This is bounded. So then turn around, there is C, that is the contrast of my region. I want to increase it, I'll change it to CE, which is the enhanced value. Turn that equation around, there is a background. So my starting pixel could be somewhere here. So this is the seed. So there is B, and there is contrast. C becomes CE. So using B and CE, you find the new value for F and put that to the seed pixel location, which is that. Just turn that equation around. So only the seed pixel and the redundant seed pixels, which are all the pixels inside the foreground region that have exactly the same pixel value as the seed, they all get this output. Other pixels have to wait until they become the seed and a region is grown and all that. Computationally intensive, but the results were interesting for us, and radiologists also approved of the result. So at first we used various functions. We said let CE be some function of C. So instead of just is some, oh, F is already there. So we will have to use something else. So this f of c. So some function, some mathematical function of contrast, so that we can specify a lookup table or some transform of contrast. It's a contrast transformation. At first I used square root so it would increase and square and everything, and it was too much. So then we said, well, if a region has good contrast already, there is no need to increase the contrast. Only regions with poor contrast need enhancement. And those that are below a certain contrast level, we are not going to enhance them. So we said, if you take the straight line diagonal as a reference, the input contrast is from 0 to 1. The output is also between 0 and 1. I'm showing here 0 to 0.6. So the straight diagonal line would be no change. So at the top, when the contrast is more than 0.3, we're not changing it. We said, well, it's already a good contrast there. And below 0.02, we're not going to change it. Internal structure or noise, we don't know. And then here we increase the contrast, and then we reduce the enhancement. So this is the contrast enhancement curve that was developed by my grad student in his thesis work in consultation with radiologists, and we tried different functions and showed them the results, and this was found to be acceptable. So a few examples, that same microcalcification example. This is adaptive neighborhood contrast enhancement. This is gamma correction. This is unsharp masking. So which is good, which is not good, that's up to the radiologist to determine. But you could take a look at them and judge yourself. Of course, we claim that is the best because we developed that. But then we gave these images to the radiologist and multiple radiologists. A few examples. If you apply histogram equalization to the whole image, this is washed out. By the way, the procedure was applied to the entire image. I'm showing only this part with calcifications, but the entire image was processed. This is only 43 millimeters by 43 millimeters in a mammogram that is typically 20 centimeters by 25 centimeters. So histogram equalization sometimes washes out small details because the probability of occurrence of those values is so small. When you add up the probabilities and do the transformation, those details are lost. Here's a case with a dense mass, and there is something else here which is not very clear, and the result of enhancement. Now, radiologists did not want a drastic enhancement. The previous methods were doing very drastic enhancement, and the mammogram would not look like a mammogram anymore. That was the problem. When I started working on medical image enhancement, we went and asked radiologists, we know some image processing, would you like us to do something with your images? And we asked, how about chest x-ray images? I said, no, chest x-ray, I can read everything. Images of the extremities, hands, legs. They said, no, all of those is very clear. I don't need your help. How about mammograms? Mammography was new at that time in 1980. Screening programs were just beginning. Well, mammography was there before, but screening programs were beginning. So mammography was being used on a large scale. And women were afraid to go to get their mammograms done because of X-ray dose considerations, compression of the breast, and so on. So the popularity of screening programs had to be increased, and there were big campaigns. Every state and province and country they're all promoting mammography and trying to demonstrate its safety. Eventually, better and better films were developed, radiation dose was reduced, and now with the same dose as for standard mammography, there is breast tomosynthesis where sectional images are obtained. Not CT reconstruction, but some planes. So mammography has changed quite a lot. From film, it has moved to digital. Digital gave much more contrast, so we don't need this anymore. With digital mammography, there is so much contrast and improvement of quality. All of this is outdated. But still, there is a certain concept as to how to enhance contrast of regions. So this is one of those examples from the Foothills Hospital in Calgary, and also we got several hundred images from the screening program and enhanced them, showed them to the radiologists. They did analysis before enhancement, after enhancement, using different enhancement and printing procedures. So this is a part of a mammogram with a benign cyst, and that is after enhancement. So how do you evaluate this? In our lab, Dr. Desertil, who was our collaborator in radiology, experienced in mammography, he came and looked at them on computer monitors. We also printed back on film in those days. Monitors were not good to display mammograms. And he analyzed them and gave us some detailed comments, which we published in that paper. I won't go through all of that. In the textbook, I have given the description of the enhancement by the radiologist. But in most cases, he was positive in the sense the enhanced image showed some details that were not obvious in the original. And then we did another study where we got a few hundred images, enhanced them, and we had to print back on film. The monitors were not good. And then we had 5 radiologists come and interpret each one of them and rank them as they do in the screening program, and then analyze their ranking through what is called receiver operating characteristics, or ROC analysis. So we showed that the ROC curve area increased slightly with enhancement. We gave the program to several other researchers, and in particular at Cleveland Clinic Foundation, they did a study where they showed several enhanced images, including ours, to radiologists and asked them, they didn't tell them which is which, they said, which is the best one of all of these. And in images with calcifications, they chose the output of this method. For images with tumors, they said the original was the best. So it depends on what is present in the image and what is not obvious and what is obvious. If a tumor is so big and clear, you don't need enhancement. If there are small microcalcifications hidden under dense tissue, then this helps. So it's not, just because it works, it doesn't mean it must be used everywhere. Each technique has an application for a specific situation. But we did one more thing, which was a bit unusual, and the reviewers were happy with this. We got some good comments. And that was, how do you characterize this enhancement in an objective way? Right at the beginning, I said subjective versus objective, qualitative versus quantitative. The radiologist looked at the image and said, well, there is increased contrast of this. That is qualitative or subjective, according to him. You may say, well, they're the same and it's not good. Or somebody else may say something else. But that's subjective. Objective, we said, well, contrast is what we are trying to increase. Can we measure contrast again? In the process of enhancement, we are measuring the contrast of every region that we obtain by region growing. They are not parts of the image. There are some patterns in the image. We don't care what they are, but contrast. So we got that contrast for every region in the original image. So we made a histogram of that. Contrast is between plus and minus 1, according to that equation. It's very rare that you will get a contrast of 1. The contrast is mostly between plus minus 0.4, 0.5, something like that. I'll show the histogram. So how many regions have this value of contrast? So make a histogram. And that was for the input, it's already being done. For the output, we cannot use the same enhanced value CE, because if you grow regions again on the output, the regions will be different because other pixels have been modified. So instead of using that enhanced value, we said we will do region growing all over again on the enhanced image. And for every region grown using the same algorithm, we compute the contrast and make a histogram. So we have contrast histograms that we call PCI. Contrast values have been binned into little segments of the value range from 0 to plus minus 1 rather. So we have n bins in the range plus minus 1, and the moment you take the variance or second moment. CI is, okay, CI square PCI. If you want, I can subtract the mean, but we didn't do that. It's a second moment. PCI is a normalized number of pixels, or like a probability of the region with the contrast CI. So that's the number of times the value CI has occurred. Low contrast image will have a narrow histogram. High contrast, there will be a broader histogram. So this is a measure of the spread of the histogram. The broader the histogram, the better the overall contrast of the image. So this is the from minus 0.2 to plus 0.2. This is the histogram. Zero, of course, they're not interested in zero contrast. So this is the histogram for the original image. This is, let me go and check the, yeah, that is for adaptive. That is for one original entire image, mammogram. And this is after enhancement. I mean, there are more values here. I'm showing the histogram only for plus minus 0.2. So you can see there are more regions with this contrast, and there the contrast ended it at about 0.1. And here it is going to plus minus 0.2 and more, actually. I'm not showing that part here. And this is with gamma correction, not bad. And this is with unsharp masking. But the moment values for the original was 3.71, adaptive neighborhood contrast enhancement 6.17, and the next one is gamma correction 3.2, unsharp masking 4.4. So unsharp masking has resulted in a slight increase in that value of M2, but the adaptive neighborhood contrast enhancement has a higher value of that moment. So now we can say, based on that moment measure, we are getting an image with more contrast over more regions in the image. Interestingly, this paper also got a large number of citations in the Transactions on Medical Imaging. So that is objective analysis of enhancement. And before that, I showed subjective analysis. All the other pictures I showed, I simply said this is better, that is not, and you can judge yourself. In this case, the radiologist analyzed those images, but he is our colleague and friend. So I'm sure he would be subjective, or he would be as objective as possible, but that analysis is still subjective, no measurements. This is where some measurements are made. So like this, you need to have not this same, but some other suitable method to characterize what has been achieved in a quantitative manner. So you can put a number to it and say, this is how much we have gained. Okay? So that finishes the chapter on enhancement. So we have gone through the first 4 chapters, skipping the first chapter, chapters 2, 3, 4 of the book. I have gone through some parts a little fast, where I felt perhaps discussing those minor details or minute details would not be suitable in such a presentation. And some I have gone through in some more detail, but you should read the notes, or better read the book. There's more discussion in the book than just the notes. And for my students who used to take the course, I would always say, don't just read these notes, but read the textbook and read other textbooks also. So when we were engineering students in Mandayam, we would pool our money together. Books were expensive, especially those by US authors reprinted by Wiley India or Prentice Hall India or McGraw-Hill Kogakusha in Japan, but they were expensive still. So we'd pool our money. For every course, we would buy 2, 3 books and share. So that is important for anyone who wants to study, to get multiple sources of multiple views of that subject. Gonzalez and Woods or Pratt, or there are so many other books now. So you should refer to many of them, and they will have other methods and other ways of thinking. So you can get all of that and then form your own opinion and your own understanding of that topic. So just this will not help. It'll help a little, but you need to have more than that. Do you have any questions before I switch the topic, or any comments? I'll pause for a little while so you can think about any questions or comments or anything you want to say. Yeah. Please speak up. The others can hear too.
So usually when we look at mammograms, right? Okay, mammography in general is kind of a saturated research work, like you said, saturated, like the work is saturated.
The work, you mean in the field?
Yes.
Publications, yeah.
Saturated. So how about anything in thermography? Because do you have any stuff like how you go about acquiring the data sets or something like that, as in regards to breast and mammography?
Yeah, tomography has not found application in breast imaging because of the radiation dose. MR imaging has been used, but MR in Canada and the US is not so easily accessible. And here you can access, but it's expensive. And there are some special coils and systems, but MR doesn't show certain details that are visible in X-ray images. So even MR, it's a question of availability, cost, and screening versus diagnosis. Screening, the technique has to be fast and not too expensive for mass screening. When something has been found to be suspicious in a particular person, then that person is sent for further examination. Then it is called diagnostic imaging. Then they could spend more time, effort, money, whatever, because something is suspicious and they want to confirm. So it is typically not by mammography alone. Mammography in screening, suppose it causes some suspicion, then ultrasonography could be used. And some needle-based samples, needle aspiration samples could be taken, and biopsy could be done. But if that is not conclusive, then other modalities are used. Tomosynthesis is being used. Interestingly, one of my projects when I joined Dr. Gordon was to do tomography using projection, ordinary X-ray film images. So I took a number of images of various samples, including a frozen mouse, a dead frozen mouse. I said, I'm an engineer, I'm not going to chop this up. But anyway, I had to take X-ray images using the overhead X-ray on a bench and then at different angles. And what we did is similar to tomosynthesis. We didn't call that so. We should have called it and patented at that time. We didn't. So tomosynthesis can be done, but that nowadays the total dose of tomosynthesis where 11 to 15 images are taken at different angles from the overhead, but over a limited angle range. So you can get a few sectional planes. And that is slowly coming into screening. And their image processing is still being explored. Because analysis of those images, they're like mammograms of thin slices of the breast. So they are similar to mammograms in appearance, but details in different planes of the compressed breast are separated. So we should get better results in detection. They may not need enhancement. And CT and MR images, in most cases, don't need much enhancement, but detection and analysis is where more work is being done.
Maybe I put it differently. So what I was actually asking is like thermal imaging, okay, of the breast, because actually there is a funded project like I'm interested in. So these guys they are from Saudi, so they are willing to give us a thermal camera and some stuff, and we sign an MOU just to go get those imaging done. So for that we need oncologists in between. So my question is like, how is the research over there in the US? Like, I mean, much emphasis is being placed on that, or we should think of a different modality?
Thermography was explored substantially in the 1970s and 80s. So I have studied, when I started working on mammography, I studied a number of papers comparing thermography, transillumination with light, and what else? X-ray imaging, ultrasonography. At that time, thermography did not work well. Thermography could detect advanced tumors, large tumors, but not others, and not calcifications. And the resolution was poor, so that fell out of favor. Even ultrasonography is used mainly to guide the biopsy needle and get a sample out. Ultrasonography by itself is not adequate as a diagnostic tool, because there again you can find tumors, yes, large tumors, but calcifications and so on, no. And it is very much operator dependent. The skill of the operator is important. Now I have read some articles that say new thermography systems are much better with substantial developments in military applications of night vision systems. I have not seen those. I have not seen recent papers on thermography. Perhaps if those new thermal cameras can give better images with better resolution, you will be able to capture better images, and their enhancement perhaps would be required. Different type of analysis would be required because the patterns are different. You won't see ducts in all such fine detail, but you will only see certain objects. In Calgary, one of my colleagues, Dr. Elise Spear, she is working on microwave imaging, and that is gaining more popularity. Microwave imaging of the breast and microwave imaging in general seems to be gaining more popularity. And the advantage is it's non-ionizing radiation. Thermography, of course, is safe. Electromagnetic radiation, microwave, there will be some local heating and other effects. Some energy is deposited, so something could happen, but not as bad as ionizing radiation. So, what is that? Microwave imaging has picked up. In our new book, we are writing a little bit about that. Microwave imaging and what was it called?
Terahertz related. Terahertz.
No, impedance, electrical impedance imaging. There was electrical impedance tomography that was investigated in the 80s. Microwave imaging also measures certain electrical properties of the tissue. But you're not applying electrodes, you're letting an electromagnetic wave pass through. With microwave imaging, you're at a higher frequency than typical, you're at a higher frequency. I'll just stop there. So perhaps diffraction is not a serious issue. With thermal, there could be more diffusion, and that affects resolution. So you need to go to a higher frequency, not as high as X-rays, a little lower. Thermal is much lower, right, in terms of frequency. So those are the things you need to consider. From what I have seen so far, microwave imaging seems to be gaining popularity. And they have advanced and they are doing some field tests. I'm not sure how the diagnostic interpretation has been done yet, but that's very new. Does it answer your question? Okay, thank you. Anything else? Oh yeah.
Abnormality itself, there are different.
Start again, please.
Within one image itself, the abnormality may have different contrast level.
Yes.
So maybe I have missed something. What is the effect of this adaptive techniques on such abnormalities?
Yeah, I have not shown all the examples. Within a mammogram, there could be calcifications that are large and they are typically benign. Microcalcifications, like what I showed, they are very small, could be a fraction of a millimeter each, but still the shape is important, even though when they are so small, and the density, how many of them in a given area. Masses, dense masses, cysts that could be fluid-filled or solid, masses that are benign or malignant, masses that have sharp boundaries are usually benign, masses with spiculations and blurry boundaries are typically malignant. What else? Calcifications within ducts and overall breast density, but that's for the whole breast, not local patterns. Those are different aspects. Dense tissue versus fatty tissue. How much of the mammogram area is covered by dense tissue versus fatty tissue versus fat. So for that, we did some Gaussian mixture model analysis, and I think it'll come up later on in the next chapter. The enhancement perhaps is required only for fine objects of low contrast. Large tumors are clearly visible, and that's why we cut that contrast enhancement and said after 0.3 or 4, there is no need for enhancement. So it remains the same. So it depends upon the size and shape of the region and its contrast. And there are regions of different size and shape. For different types of signs of breast cancer in mammograms, then we need different algorithms to detect each one of them. One technique cannot detect all of them. So in the next chapter, we will look at detection of calcification, detection of tumors, and later on analysis of asymmetry, detection of architectural distortion. We will see all of those later as detection, not enhancement. The detection procedure itself may have some enhancement capability built in, but we're not going to show that image. If you use a Gabor filter, it's a bandpass filter, so it does some enhancement and then gives you the output, which is extracting the features of interest, not enhancing. You want to call that enhancement? You could, but it's more of extraction or segmentation or detection. So, yes, there are, in any given image, there could be multiple types of signs or symptoms of the disease you are trying to catch, breast cancer or whichever. In the colorectal system, there are algorithms for computer-aided diagnosis of colorectal cancer to go through virtual colonoscopy, CT images, and detect polyps and so on, or bleeding. So depending on the application, there are different signs, and you must tailor your method for each one of them. And detection, enhancement and detection could be combined. If the enhanced image is not to be, if the radiologist or the user is not interested in viewing, but simply say mark the image and tell me where to look for some suspicious thing, then it switches to detection, possibly with false positives, but you say, okay, look here, look here, look here. The rest of the images, you don't have to bother with that. So enhancement is a step where if you give the result to the radiologist, that's one thing, or the user. If you take that image and go to the next step yourself in your algorithm, that's a different, you could take a different type of result to the next step of detection and analysis. So the next, yeah, okay. Anything else?
Maybe part of many screening programs as we have collaboration with medical institutes. So for single patient itself, both the breasts may show different abnormalities. Is there such a case or
different abnormalities? I don't know, but tumors and calcifications do not necessarily show up in each breast. No. Within a given mammogram, there could be multiple tumors, and one could be benign, one could be malignant mass, and there could be calcifications. But yeah, that means one breast shows the disease, the other doesn't. Is the other one normal? I don't know. There could be something else there. But a given image could show multiple signs for sure, and one breast may show the signs of the disease, the other may not. Okay? Okay, just before we break, what we have seen so far is what I would term as image processing. We are processing the image, we cleaned it up, and we removed the noise and enhanced and so on, and the result is an image to display. Either we look at that, or somebody else looks at it, the user looks at it, or it goes to the next step of analysis. The next step is what is called segmentation. In this context, I would call it detection of regions of interest. There are certain regions that we are interested in and certain other regions that we may not care about. Background or just normal tissue, if you separate normal tissue patterns from what could be potentially abnormal. When you do that, you may get parts of the image, but they don't represent the full image anymore. It's sort of in between image processing and analysis. Once you extract a region, detect and say, okay, this is what I want, and analyze it further and extract features, compute shape, texture, and whatever else you want to compute, then you just get a bunch of numbers. No more images. So even at the step of segmentation and detection, you get parts of the image that the user may not be interested in. If you take that out of the context, the tumor is just like some round object or irregularly shaped object, that may not be really like the original image. It has no bearing if you take it out of the context. If you take just my eyeball out of this and show us a picture, it doesn't look like a picture. It could be anything. So the result of the subsequent steps will not be an image anymore, and this is where I would switch the terminology from image processing to image analysis. We, or our algorithms, will be analyzing the images and extracting parts of the image and computing features for further analysis or classification perhaps, or whatever the next step is. There are more steps. When I used this term, there were some in the audience that said, no, computers cannot analyze, only human beings can analyze. I said, no, this is analysis, the next step. And then I went back and saw Papoulis has a book on signal analysis. I said, fine, if he could call it signal analysis, I can call this image analysis. So there is that distinction one could make between processing an image and getting another image, processing a signal and getting another signal, and then processing that and getting some numbers, some features. And then you just get a bunch of measurements. And those are important. If you design them properly, they can help you in diagnostic applications and classification. So that's the end product. And you will see the end of all of this falling together to show some nice results in some of the research projects I'll demonstrate at the end of the course, but you have to wait. I taught a course once on digital filters and started with the Fourier transform, Z transform, Fourier transform, Laplace transform, and so on. They said, I got bad comments back, students saying, this is not a course on transform, this is not a course on Fourier transform, we want to learn filters. I said, wait till the end. And then at the end, we saw the filters and everything, and then they said, at the end, I learned everything. Yeah, you have to wait, you have to go through the process. You can't just say, this is a filter without knowing the background, right? So hopefully at the end, there'll be some nice things.